Hello friends, welcome back, and we are now closer to our sessions in this one, fundamentals of air pollution. In the previous lecture I discussed some of the terminology that we use in the radiant energy, and if you remember I talked about the different terms that are there. I talked about the ephemer, energy, flux, irradiance, monochromatic irradiance, and then radiance. And I also talked about that what is the energy that is actually measured by the satellites, radiometer, and then which is actually given by the Planck's law. And then we also discussed that what is the actually, if you see the graphs, mostly it is kind of irradiance versus the wavelength that is plotted, and the different units we also talked about. That is very important, because if you are going to give any competitive examinations, you would probably have many of these things in the lectures. Yeah, so just I am continuing with the previous one. Although I talked about the irradiance in details, it is actually radiant flux per unit area, and radiant flux was actually dq by dt, and now you have another area dA. So this will be the terms, and then dq by dt is actually like joules per second. So you have the unit like watts per meter square. We calculated this number. This is the unit actually. In some of the text, this irradiance is called radiant flux density. Remember, whenever whenever we measure any physical properties, it's whenever you take by volume, anything you divide by volume, then it is actually becomes density. Like you have mass by volume, so this becomes mass density. But in the physics lectures, if you remember, especially the electricity and other things, if you take anything upon A, it is generally defined as intensity, I upon A, energy density. What do you call? So this I think some terminology are there. I just put the corollary here. So you just remember here, for example, here radiant flux, okay, flux per unit area. This is actually defined as a irradiance or radiant flux density. So here density, it is no meter cube, it's only meter square, but just it is actually defined in some of the text. So please be careful with that one. We also calculated the irradiance of electromagnetic radiation that is passing through the outermost limit of the visible disk sun, and we assumed that sun's radius is about 7 into 10 to the power 8 meter, and we calculated that this is the actually radiant flux that we had from the sun, 3.9 into 10 to the power 6, and if you just multiply by its surface area, which is actually 4 pi r square, you will get actually like 6.34 into 10 to the power 7 watts per meter square. But and this is actually like you have here is shown in the pictorial form. So you have sun and you have a surface, radiance flux incident on the specific in a surface per unit area is actually becomes irradiance, and you have surface. And similarly, if you talk about when the radiation source is sun, how much radiation is emitted per unit area. Be careful again in some of the text when we will do some calculation that what is the radiation that is reaching on the earth surface, we will use pi r square. Sometimes we will be using 4 pi r square. So just remember, this is actually cross sectional area, and this is actually the surface area. So whenever you have to calculate any property that is related to the surface property, then you have to use the area 4 pi r square. But when it is the radiation that is falling on the earth surface, then you have to use pi r square itself, cross sectional you have to use. So we will see this one in coming slides. Yeah, it is there actually. Okay, so now if you calculate, we know in equilibrium condition that solar irradiance that is arriving at the earth can be calculated by realizing that the flux is constant. Okay, so if you assume that the flux is constant, and flux will be actually what is called So you had energy, flux, and then irradiance, and then monochromatic irradiance, then you had radiance, right, ephemer. So energy and then flux, you assume here that the flux is constant. So this means watts, and what is the energy? Flux is actually like watts, okay, and irradiance is actually per watts per meter square. Just remember the units, okay, that will be easier to calculate these things. So if the flux is constant and there is actually equilibrium, what you call equilibrium between sun and earth, the temperature equilibrium, okay, what will happen? The energy that is emitted from the earth, it should be equal to the energy that is coming from the sun's surface, okay. So this is these two has to be in equilibrium, otherwise this system will not work, okay. So when we talk about the equilibrium between sun and earth's flux equilibrium, you can say, so what will be the energy that is emitted by the earth's surface? And now you have to remember here, now it is the energy, and we assume here that both earth and this sun are actually acting as a black body. Both earth and sun, they are acting as a black body, and then if you just calculate what is the actually flux is constant, and if the flux is constant, this is actually the flux, and we assume that this flux is constant. So we can calculate flux is actually irradiance into surface area. So E is actually the irradiance, and from the earth surface, 4 pi r ES, ES means stands for the radius of the earth surface, or earth actually, and then you have energy from the sun surface, and you have 4 pi r S square means radius of the sun. And if you just put these numbers, what will happen? And we know that this is the radiance between the ES is actually mean earth to sun distance. So this is from, you have to calculate flux, constant flux that is arrived at the surface is constant. So what is the radiant flux that is from the sun itself? So these two has to be in equilibrium, and we assume that is actually 4 pi RES is actually 1 astronomical unit I talked about, and since they are actually at 1 astronomical units, okay, so this will be like 4 pi r square. So you just put these numbers here, you will be able to get that earth surface, that the irradiance of the earth surface is actually 130 watts per meter square. So you have to just play with these numbers. These are very small calculations, but what is more important, that energy that is emitted from the earth surface and what is actually that is there on the earth from the sun surface, and what is the irradiance of the earth surface. If you just calculate and you assume that they are at RES distance, earth and sun distance, so the energy reduces by 1 upon r square, and if you assume that when the energy should be constant or flux should be constant, you will be able to calculate this number. So energy, so this is what is this E here. E is actually in principle irradiance. What is or irradiance? No, this is not irradiance, because if it is irradiance, it will be watts per meter square per nanometer. So this is not actually. So it is not irradiance. Energy, this is the flux actually. This is the flux. What is this is? So this is the flux. The solar irradiance that is arriving at the earth can be calculated by realizing that the flux is constant. So the flux is, when the flux is constant, you can do this calculation. And when I talk about another terminology, it was actually monochromatic. Mono means one, as we say, and chromatography likes wavelength, lambda, so one wavelength and irradiance. So E lambda, you can just, the irradiance per unit wavelength is defined dq by dt by dA per unit wavelength. If you just talk about it, it becomes irradiance. Okay, so this is irradiance that is there, and irradiance will have the units of watts per meter square. So you just see watts per meter square, and then you have per nanometer, or also sometimes it is written as watts per meter square per centimeter inverse, or some, because it is the, you can write it in the terms of wavelength. Okay, so you can just, if it depends on the whether the wavelength is given in nanometer or centimeter inverse, but usually this is confusing, but in we have very less choice, because some of the text they will use this watts per meter square per nanometer, sometimes you will see watts per meter square per centimeter. So but anyway you can just calculate this one, and since I talked about this one, so if you have irradiance in this direction and you have lambda in nanometer, this unit was watts per meter square per nanometer. Okay, and then we had this kind of graph. So you can in principle calculate, you can integrate this area. Okay, so integration of, this is for example E lambda, and integration of E lambda d lambda, this will give you the total irradiance actually. Okay, so this will, by definition you will get the total irradiance is readily can be seen is equals to integration, where lambda is varying from 0 to infinity. In principle it is not 0 to infinity, you can calculate say somewhere around 200 nanometer, it goes up to say 2600 nanometer, we remember, and the number was here like this, maximum radiation, but this radiation can be actually up to 4000 nanometer from the sun. So you can calculate. In general, the irradiance upon the element of surface area may consist of contributions which come from infinity of the different directions. So this means it is coming from all the surface area, they are coming from all the directions, and when they are coming from all the directions, then actually you have to introduce another one. So in that case what you have to do, surface area, and then we will define this one, what is the energy that is falling on a particular solid angle, then we will see another terminology here. Yeah, so there are different types of solar irradiance we talk about, and then it's actually direct, categorized into three terms generally. So this is, you have direct normal radiance, this focuses on the direct beam of sunlight that reaches a surface perpendicular to the sun's ray. So when you're actually, it is directly when the if you are what you call, if you are focusing this pyranometer, I think it's called, perpendicular to the radiation of the earth, radiation of the rays, and then it is their surface, that the sunlight that is reaching on the surface is perpendicular to the sun's rays. This means it will exclude the diffused and reflected radiations, because in that one you will see less path. And diffused horizontal quantifies the scattered sunlight in the sky, omitting direct and ground reflection. So direct and ground reflections, when it is emitted, then it is called diffused. You have global horizontal index, this represents the total solar power received by the horizontal surface, accounting for the direct sunlight, diffused radiation from the sky, and ground diffraction. So there are different kind of instruments that are there. So based on the instruments which, so but you should remember that DNI measures, what DNI measures, what does diffused horizontal radiance means, and what is the global horizontal irradiance. So you can see this one. So in the previous lectures, in the previous slide I showed that they are actually measured, irradiance is coming from different directions. So different directions means you have angle, and this angle, when you have 3D object, this angle is generally called as solid angle. Okay, and within a say d omega, omega is generally taken by this one. So what in that, for an infinitesimal solid angle d omega, how much is the irradiance that is coming, is actually called as radiance. So radiance is actually nothing but irradiance per unit solid angle. Okay, so now radiance was dq by dt by dA d lambda, this was there, and you have to introduce another terminology by d omega. So this means the unit will be watts per meter square per micrometer per steradian. So watts per meter square per micrometer per steradian. STR is usually written. So this will be the units. So here I remember that I have put the unit of the wavelength is micrometer. So if you are putting in the micrometer, it will be micron. If you are putting in the nanometer, it will be in nanometer. But the solid angle is generally given in the terms of steradian. And this quantity is often referred to as intensity. Now there is another terminology. If you just remember in the previous slides, we discussed that this is actually density, flux density. There was actually flux density. Okay, radiant flux density. And this was actually radiant flux density was defined as irradiance. Okay, remember. Similarly, radiance is also defined, sometimes called as an intensity. Okay, and is denoted by letter beta. I mean B. It's a different terminology. We will see this one. You can use this one. If the zenith angle theta is angle between the direction of the radiation and normal to the surface, then component of radiance normal to the surface is given by I cos theta. You can just remember I talked about in the solar zenith angle and other things. So in that case, you have to integrate. It will be I cos theta d omega. So you will have another where spherical cos and where d omega is actually its different units is written. It is dw is written, actually it is d omega, and d omega is actually sin theta d theta d phi. So this is actually spherical coordinates. This is little bit complicated. You have to understand some of the mathematics here, but I think it's not very important to remember all those mathematics or do the calculation. Just remember that that what is the actually irradiance and radiance. So just remember the radiance is irradiance per unit solid angle, and then if you have to do calculations, you have to integrate like be in the for irradiance be integrated over the wavelength. Here you have to integrate over the solid angle. And there is actually isotropy radiation. Iso means same, and the name says iso means same, okay, and tropic means isotropic means same radiation, you can say. So radiation whose radiance is independent of direction is called as isotropic radiation. So in that case, this if you integrate this function, okay, you will be getting pi, okay, circle. You will have kind of complete circle. So you just remember this was theta, and if you just see this one, theta is calculated to the radian, and then pi will come here. So in that case, integration over d omega can be readily shown to equal to the pi, and E is equals to given as pi I. So this is isotopic in case of isotopic radiation. So sometimes it is asked that what is the radiance, what will be the value of the radiance in case of isotropic radiance. So it will be pi I, where I was irradiance, okay, pi times I. Now the concept comes about the other things, although I have been discussing about the black body. So what is the black body? Black body is an idealized physical body. So this is actually in principle they do not exist. These are actually idealized physical body that absorbs all the incident electromagnetic radiation regardless of the frequency or angle of the incidence, and emit electromagnetic radiation in the thermal equilibrium according to its absolute temperature. So two things are there. This is actually 100% absorption of EMR, okay, number one, and number two is actually that the radiation emission is actually is given by the absolute temperature, okay. So it depends on the temperature that how much emission will be there, and we will see that this emission actually is given by sigma T to the power 4. We will come to that one. So So this means if you consider, and that's why kind of black holes in the system we discuss, black holes are the places where all the radiations, anything that is actually goes there, because it has, so you can just imagine that anything that passes to the vicinity of the black hole, everything will be captured by the black holes. So there will be nothing actually that is coming out. So it has so high gravity. Similarly, when we say black body, it's terms in the terms of energy actually, and this means that it absorbs all the radiation, electromagnetic radiation, and it will emit the electromagnetic radiation according to the absolute temperature. So this is the only two things that you have to remember. And then the characteristics of the black body: it emits radiation at maximum intensity possible for a given wavelength. So you will have something like we will see this one, sigma t to the power 4, but there will be a lambda maximum, which is actually Wien's displacement law we will discuss. Okay, so this we will discuss again, lambda, the maximum intensity at a given wavelength it will be given, and it will completely absorbs all the radiations. And then this emission of radiation is, if you just remember, it's only dependent on the absolute temperature of the black body, and this is given. So three characteristics you can remember: that it absorbs all the incidence electromagnetic radiation, it emits the radiation at the maximum intensity possible for a given lambda. Only one wavelength will be there where it will be peaking the emission, and then the emission will be given will be governed by that absolute temperatures. So if you see this one, these are the two very important black body emissions from the sun, and if you see this, actually sun is emission is actually like peaking somewhere around 0.5 micrometer. I am sorry, I am not able to draw it very well. So this is here, and if you see for the black body here, it peaks around 10 micrometer. And this is where it's very important. So this is, if you see this sun's radiation is actually say around 200 nanometer to 4000 nanometer it covers, and this is that's why it is called short wave radiation. Okay, and when the Earth's emission is there, it's actually between 4 to 40. Okay, so 4 to 40 micrometer, and that's why it is called a long wave radiation sometimes. So sun is actually emitting in the short wave radiation, whereas the Earth is actually emitting in the long wave radiation. So just remember, sun is the energy of the sun. When you see it as a black body, the radiation is basically in 200 nanometer to say a little bit, you can come down to 100 nanometer or so. So it's like 200 to 4000 nanometer, whereas Earth is actually emitting between 4 to 40 micrometer. And then there is actually very important law that comes here, is Kirchhoff's law of emissivity. So so we remember that one, that the emission, black body emission is actually is temperature dependent. We remember that one, and if you just remember, Kirchhoff's law states that for a body, and here means we talk about black body only, in thermal equilibrium, the emissivity of the body is equals to the absorptivity of at a given wavelength and temperature. So if you just keep the same wavelength, the absorptivity and then emissivity, these two will be same. This is very important. So, and this is why it is called a perfect emitter. Okay, and not perfect emitter, and when this value becomes 1, they is usually called as a perfect emitter. Perfect emitter or absorber. Okay, so the emissivity of the black body and then absorptivity of the black body will be same. This you have to just remember this one. And what is the emissivity? Emissivity is how efficiently a body emits thermal radiation compared to a perfect black body. Sorry, this actually, if it is actually like perfect emitter becomes 1, and when it becomes 1, then it will be actually like a black body. So in case of black body, this epsilon and alpha is considered to be 1. Okay, so emissivity is actually efficiency of a black body to emit the thermal radiation compared to a black body. So if the value is close to 1, this means that emissivity of the body is actually similar to black body, and in that case you can say that the body can be treated as a black body, and this value ranges from 0 to 1, and for black body epsilon is 1, and this means it emits all the radiations, and it's a perfect reflector. So it reflects all the radiations it emits. Okay, so it's a perfect reflector, so it can actually emit all the radiation and it can absorb all the radiation by reflecting nothing actually. Okay, then absorptivity is the fraction of incident radiation absorbed by the surface. Again the value ranges from 0 to 1, and then black body, for black body alpha is equals to 1, perfect reflector alpha is 0. And thermal equilibrium, the body is in stable states where neither gain or nor the loss of the energy. So when we say thermal equilibrium is actually a state in which the body neither gains the energy nor loses the energy. So materials, it has been observed that the materials which are strong emitters at a particular wavelength are also strong absorber at that wavelength. So we have to consider epsilon lambda is equals to L lambda or alpha lambda, L absorptivity, which is the fraction of incident radiation that is absorbed by the surface. Okay, and emissivity is given at the wavelength defined as the ratio of irradiance of the body of the object to the irradiance of the black body. So we have to compare here the black body. You remember in the Beer's law we also use this similar terminology I upon I0, but here actually this was incident radiation and this was the transmitted radiation, irradiance. Here you can say here actually it is compared with the black body. So that there is a difference actually. When you compare the emissivity or the absorptivity, it is always compared to the black body. So some of the significance of the Kirchhoff's law, this relates to the absorption and emission of the radiation, explains why good absorbers are also good emitters. This is basic for understanding of black body radiation and Planck's law, which we will discuss later, and this can be used in different applications like designing thermal insulation, infrared imaging, astrophysics and climatic studies. This has a wide application. This is a very simple law, Kirchhoff's law, but it has a wide application in this one. Yeah, I talked about that black body radiation. You can talk about this is idealized body object absorbing and emitting radiation at its maximum efficiency. Basics for the Planck's law and the Stephen-Boltzmann law, because I talked about Stephen, there will be epsilon sigma t to the power 4, so epsilon is taken 1. Thermal imaging, emissivity of the surface affects infrared camera reading. Then astronomy and climate science, this is understanding the energy balance in the stars and planets. We will see in the climate science how it can be used. And then there are actually like industrial applications as well, heat treatment of the material, designing of energy efficient coating as well. So there are very important things. And yeah, just black body is, when you say when you compare a body and black body, so black body is a kind of a special case which is actually perfect absorber, so alpha becomes 1, and perfect emitter, so alpha and they both becomes 1, 100%. And this of course this emits maximum radiation at a given wavelength, at a given temperature, and the wavelength can be calculated. And real surfaces, the deviate from the ideal black body behavior, so you will not have alpha and epsilon close to 1. Most of the time for these real bodies, the epsilon and alpha will be less than 1. Okay, so I hope that you had some concept about black body, Kirchhoff's law, absorptivity, and then kind of emissivity. So in this lecture I think I will now discuss in the next lecture Planck's law and Stephen Boltzmann law, and then we will see that how the thermal equilibrium temperature, the thermal equilibrium between Earth and Sun surface is used to calculate the temperature of the planet or Earth surface. So I stop here. Thank you very much.